All right, let me introduce our next keynote speaker. It is Professor Nurit Agam from the Gurion University of the Negev. Well, when most of you complain in the morning about that the morning coffee gets cold, well, Nurit has dedicated her whole career on the fascinating exchange of heat and water, mainly in the soil and atmosphere and plant interface. She's leading the micrometeorology lab at the Blaustein Institute of Desert Research, studying everything from sand dunes to dew formation and even the growth of grapes. So, what I find actually personally most impressive is that she's managing to do both, being a mother of 2 millennial and Gen Z kids, and doing cutting-edge research in one of the most extreme environments of the world. Her research takes her from all kinds of deserts, from the Negev to the Atacama to Gobi, and basically if it's hot, dry, and seemingly impossible to work in, then Nurit has probably already set up one of her sophisticated equipment there. Please give her a desert hot welcome to Professor Nurit Agam.
Oh, thank you. Well, if you only remember one thing from my talk, is it really is desert time. And I hope I will manage to convince you of that. I would like to first thank the organizers for inviting me. I'm honored to be here. Well, some of the deserts that Martin mentioned are yet to be explored. We're actually going to explore a few others, but there is plenty. So let's start. Why is it desert time? So I don't know how many of you know, but more than a quarter of the terrestrial area is defined as arid or hyper-arid. More than a quarter of the terrestrial area of the world. This is a stunning number, I think, that we're not usually thinking about. And these areas, I looked, I don't know if that was the best way to look at it, how much research is done in these areas, 2 to 3%. It's second only to oceans in the sparsity of measurements. So basically what I want to say is we pretty much know almost nothing about more than a quarter of the terrestrial area of the world. It's time that we know more. We also know that deserts are sensitive to and dynamic ecosystems, contrary to what people usually think when they think about deserts. A lot is going on, even though with a bare eye, sometimes we think, day after day after day, the same thing, nothing going on, no rainfall, no evaporation, no CO2. Well, not true. And so I think that deserts need to start getting a lot more attention. And what I'm trying to do today is to convince you a little bit about why with just tiny example. By and large, we can divide this huge knowledge gap into 2 main questions. One would be, let's study more the most pressing knowledge gaps. We know that we don't know a lot about the radiation in these areas, about dust emission, about all these big, large-scale processes, but there is also a whole realm of unknown unknowns that we don't even know what it is that we don't know about these areas. And so I want to focus on this today and do it through an example of non-rainfall water inputs. By and large, we are dividing non-rainfall water inputs into 3 sources: fog, dew, and water vapor adsorption. Fog and dew are more known to most people. Both of them are dependent on temperature. So to know if there will be fog or dew, all we need to know is whether the temperature of the air in the case of fog and the surface in the case of dew is dropping to be equal or below the dew point temperature. Just to get us to the common background, the dew point temperature is the temperature that the air needs to be cooled to in order to reach 100%. The third non-rainfall water input, which is probably the more common in most arid areas and the least explored, is water vapor adsorption. You probably now can guess this is going to be our focus. It started quite some years ago with me during my PhD. And what I wanted to do is to quantify how much dew forms on a desert soil. We know that there is a lot of dew in these environments. Specifically in the Negev, there has been a lot of research about dew. Numerous papers start by there is a lot of dew and dew is super important to this and that. How much really does it form on the soil itself? And as I said, for dew to form, what we need is that the surface will be cooler than the dew point temperature. What we see here are 8 nights spanning the dry period in the Negev. We see here the x-axis is time from 8 in the evening to 8 in the morning, so the critical time for dew formation. The y-axis is temperature, and the red lines are the soil surface temperatures, the blue are the dew point temperature. So we need to look for cases when the red line is below the blue line. Clearly, we can see that, well, except maybe a little bit here and a couple hours here, it does not drop below. So we actually figured out that there is no dew forming on the surface. However, when we took samples, the good old method that is the most absolute accurate for water content in the soil, we took samples, we weigh them, we put them in the oven, we weigh them again, and this is what we found. Every night that we went out, and here we have 24 hours, so noon to noon, 9 different days. In each of them, there was an increase in the water content of the soil, starting from the afternoon all the way until sunrise, basically. Once the sun rises, the water content starts dropping, we start seeing evaporation. It's not dew, so that led us to the understanding that what we are seeing here is actually water vapor adsorption. And by water vapor adsorption, what I mean is that we have a very dry soil, so the air-filled pores in the soil are drier than the atmospheric water content, and so there is a gradient of water vapor from the atmosphere into the soil. These water vapor molecules get into the soil and then attached to the soil particles. Do we care? And I want to point out the axis here. We are talking about, yes, a very regular increase of water content. Yay, between maybe 1% gravimetric water content to 2%, right? Going from extremely, extremely dry to extremely, extremely dry plus 1%. Do we care? So actually, I think we should care, because when we look at it in terms of energy, and this process does involve energy, because once the water vapor attaches to the soil particles, it changes phase, and phase change involves energy. And so when we look at this energy as a fraction of the net radiation, which is the available energy for all the processes, we see that it can reach up to 20% of the net radiation in quite some hours, and when it is not 20%, it may be 10%. This is not an insignificant amount. So we really need to think about that as an energy contributing or a player in the energy balance of the system. Currently, to the best of my knowledge, and if I'm wrong, I'll be happy to be corrected, none of the global models consider this process, okay? But fine, it's in the Negev. The Negev is a tiny desert. Maybe it's just an esoteric, interesting, but esoteric phenomenon. So we were wondering about that. And we wanted to explore and see how it looks like in other deserts. So the first desert we went to was actually the Namib Desert. It's a sandy and foggy desert. This is a real picture of what it looks like. So here is Namibia in the southern part of Africa. We were here at the Gobabeb Namib Research Institute, here in the Namib Sand Sea, very close to the gravel plains. And it was part of a course that I taught there with participating students from Israel and Namibia and South Africa and the US. So we had quite a lot of very enthusiastic hands to help us do the measurements. So we had a bunch of small microlysimeters, so 10 centimeters deep, 10 centimeters diameter. And what we did was, the students did, they weighed each of them every couple of hours. I think it was I don't remember if it was every hour or every 2 hours. And we watched the change in their mass. The change in mass is corresponding to the change in water. I'm sure you know it. In addition, we had also measurements of temperature and relative humidity, both in the air and in the soil. We did it for 3 nights. The whole course was 2 weeks, so we couldn't do it for more than 3 nights. The first night, we had fog. It's a foggy desert. And you can see this is us preparing for the measurements. This is how it looked like early in the morning. The 2 other nights were completely dry. You can see the difference. But when we look at the measurements, so what we see here is the 3 nights that we measured. We have here from noon to noon in each of the days, and the dotted line that we see here is relative humidity. The axis is here on the right side. Sorry, and the black lines are the cumulative water absorption based on the lysimeter's mass. And what we see here is that in each of these 3 nights, there was an accumulation of water in the lysimeters. It's true that it was a little bit higher in the foggy night, but see, this is when the fog actually started. Okay, most of the increase in water occurred actually before the onset of fog. So, and you can also see here that the total amount of water that has been accumulating is different a little bit, but is not an order of magnitude. So, what was this process? I guess you can guess. It was water vapor adsorption. How do we know? Well, we've seen that the relative humidity didn't get to 100%. And what we also know, and that was in the air, you can see here the surface temperature in all of these days, what was significantly higher also during the night compared to the air temperature, meaning that the relative humidity close to the soil was even lower than that. So it couldn't have been formation of dew, okay? So then it must be water vapor adsorption. So what we found from the Namib Desert was very encouraging, right? We saw that it's not just in the Negev that we see water vapor absorption. We actually did water accumulating during all nights, all 3 nights, okay? With similar magnitudes of water during fog and non-fog events. And so we concluded that water vapor absorption is a recurring phenomenon also in the Namib Sand Sea. Okay. Encouraged by that, we were like, okay, where next? We have 2 examples, but let's get more convinced. So the next destination was the Sahara Desert in the Western Sahara with Moroccan colleagues. And what we had there, we set up 2 different sites. One that is a little bit closer to the ocean and one that is a little bit further away. We called them campsite and station 5 just because there was a campsite at the campsite site. And station 5 is what the Moroccans called that place. And you see here these 2 lines indicating the distance from the Atlantic Ocean, because you can see the wind regime is very much dominated in this place by the trade winds that are northeasterly in this place, and not so much the sea breeze as in other places that we've been to. So we kind of took the distance from the ocean, because what we understand is that what contributes the moisture for this water vapor absorption is nearby large water bodies. So these are the distances. And in the campsite itself, we looked at both the dune. This site was a Barkan dune field, and in between them there was interdune space. So we looked at both the dunes and the interdune. And what we see here is the about 2 weeks of measurements that we had. And on the y-axis, the volumetric water content. The orange line is what we measured in station 5, and the blue line is what we measured in the interdune in the campsite. And the first thing we can see is that the water content in the soil in general was a little bit higher in the campsite. Again, the axis, right? So instead of 1.6% water content, we're talking about maybe 2.1%, but you can see that it is very consistent. But the other thing, which maybe is even more interesting, is that when we look at the diurnal cycle of this water content, we see that there are larger fluctuations actually in station 5, and larger fluctuations means larger exchange of water, and if you want, larger exchange of latent heat flux. So we actually had larger exchange of latent heat flux in the site that was further away. When we compared dune versus the interdune, so here now the dune is in the orange and the interdune is in the blue line, we can see, not surprisingly, that there is a lot more exchange between the surface and the atmosphere in the interdune compared to the dune. And of course, there is a lot more that we found there. I'm just giving you a few highlights that are relevant to the story. You can see more in the paper that just got published like 2 weeks ago. But in general, what we can say is that a nightly increase in soil water content resulted from water vapor absorption. Also here, I didn't prove it to you. You will have to believe me or read the paper. And that the trade winds, which penetrate hundreds of kilometers inland, supplied moisture from the Atlantic Ocean that contributed to this process. So now we already have evidence from 3 different deserts that this process is maybe important, but how much water are we really talking about? So we wanted to look at it also in a larger temporal scale, and this we could only do in the Negev, which is where I live. And so we have a long-term measurement site at the Mashash experimental site. We will hear about it a little bit more in a minute. For now, what we see here is the total daily water absorption that we measured. 2002 was the year of my PhD. Then 2019 onward, we have long-term measurements from, we are trying to start measuring about 1 month after the last rainfall. How do we know it's the last rainfall? We don't. But we're guessing. Why do we start 1 month after the last rainfall? Because the soil really needs to be dry in order for this process to initiate. And then we go all the way to the first rainfall in the next rainy season. So we have about 6 to 7 months of measurements that we can follow this process. You can see the empty spots here and there. This is not because there was no water vapor absorption during these days. It's just malfunction of the instruments. So you can see that the process is very consistent. Every day, there is water vapor absorption. How much? Between 0.2 and 0.7 millimeters a day. Is it a lot? No, right? But if we sum it over the whole dry period, we are now talking about 30 to 50 millimeters annually. And when we consider that the amount of precipitation in this area is 115 millimeters annually, then we're talking about 25 to 45% of the rainfall. Now let's ask again, is it a lot? We don't know, right? So we don't know what it's doing because this is water that is bound very strongly to the soil. Is it available to plants? Probably not. So they probably cannot use it. But what does it do for the biological activity of microbes in the soil? We don't know. We should know. What does it do to the CO2? Well, we know that there is a flux involved. Is it small? Yes. Is it consistent? Also, yes. Is it important? Probably yes. Okay? A lot of questions, more questions than answers at this point. So it is a significant, I believe, process. It is widespread. We know very little about it, and for sure, it is not accounted for in any global models. Could it make a difference? I don't know. The butterfly effect? We're talking about a quarter of the terrestrial area where potentially this occurs. Does it matter? Maybe. So then, I started to think about things a little bit in a more global way, and this is nice. In the last presentation, we've seen Europe in where sites are. Okay, so here is a little bit global view. What we see here is the terrestrial area color-coded according to the aridity index. Okay, so again, we're looking at the arid and hyper-arid areas, which occupy more than a quarter of the terrestrial land. What are all these dots, black dots? So it's hard to see, I know, but I think it still conveys the message. The round ones are the FluxNet sites around the world. The diamonds are LTR stations, and the X's are the location of the top 200 universities with environment or ecology programs. Clearly, Europe is densely populated with all of them. Good for you. Clearly, there is very, very, very little that is being done in arid and hyper-arid areas. Okay? Hence, it's time for desert. So I think it's not by chance that we don't have a lot of measurements in these regions. They are harsh environments. This is what it looked like in the Sahara when we conducted our research. It's quite challenging to work in these environments. We set a pole, and a week later it just fell because the dune that was here moved a meter in a week. We did not expect that. However, we do need to start learning more about deserts. So to that end, I established a consortium recently with a few more colleagues. And the idea is to set up a long-term desert climate observatory at the Mashash site in the Negev desert. You can see it here. This is the location right within the desert belt between the Sahara Desert and the Arabian Desert. And what we're going to do is to set up a fully equipped measurement observatory to look at processes from the soil all the way to the top of the troposphere. I believe we will encompass many of the parameters that has been mentioned for ELTER. Quite surely, a lot of the measurements that are in the Tereno OZCAR sites. So I welcome collaboration and of course the data, once we start gathering it, will be open for everybody. So stay tuned. And I want to just finish with mentioning the many people that took part of this work. It's not a one-person work. So my lab members, obviously, and our Namibian colleagues, Eugene Murray and Gillian Mag-Schooling from the Gobabeb Namib Research Institute, and Rani Chebuni and Lucen Bouchau from University Muhammad VI Polytechnique in Morocco. And thank you for your attention.